All right, so we might as well just start example 8 over again. We're looking on this rotated ellipse where we have horizontal tangents, and we'll ultimately want to know where it has vertical tangents as well. So I drew the horizontal tangents up there, and we said that it looks like it's going to be some, maybe like negative 0.2-ish and positive 0.2-ish, somewhere in there. But we can't just figure them out from the graph. And bless you, the graph was given to us as another fact. So we're just going to do it using calculus. This thing right here is not solved for y, and we're not going to want to solve it for y. Okay, so we're going to take the derivative implicitly, and we start by taking the derivative of both sides with respect to x. ddx, not dy dx, ddx of the left side, ddx of the right side. Two y's we have on the left side, so we're going to end up with two dy dx's. Some people might opt to subtract 2x squared from both sides first. That's fine. If you want to shuffle the terms before or after, it's kind of about the same amount of work. So from left to right, we get 4x dx dx plus, and now xy becomes a product of two variable functions, and so two factors will generate two terms. So we get 1 times y plus x times dy dx. And that's the derivative of that one term, turns into two terms. 4y squared becomes plus 8y to the first times dy dx. Yeah, and a couple people last period missed that dy dx. Also remember the right side is 0, not 3. Sometimes there's a tendency to leave it as a 3 instead of calling it 0. So the two terms with dy dx are already kind of on the left side. That's kind of convenient. We'll just factor it out then. We're left with x plus 8y. And then 0 will welcome two new pals coming to the other side, a negative 4x and a negative y. So your final answer, one version of it at least, is negative 4x minus y all over x plus 8y. And that's a good version for you to use. But if this were a multiple choice question and it said which of the following is dy dx, or sometimes even on a free response, they'll give you the answer to dy dx and they'll say, show dy dx equals this. What could also be done, though, is if you factor the negative out of both terms in the top, you could put that negative out in front of the whole thing and make it 4x plus y in the top. And when the negative is written out in front of the whole thing on the same level as the division bar, it means the entire ratio is negative. So it could actually be distributed to the top or the bottom. I wouldn't write it like that if you were going to be using it, because if you're quickly writing and you miswrite and this kind of drifts up a little bit too high, now that is being read as just a negative 4x plus a y. So instead of distributing it, it would be just the first term, and that would be incorrect. So know that you would probably have to factor it out to match it to an answer, but for safety purposes, I'm just going to let the negative stay distributed into the top. All right, so now determine where we have horizontal tangent lines. That's where the derivative is 0. So dy dx is equal to 0 over non-zero. That's going to earn a check. And now we'll set the numerator equal to 0, negative 4x minus y. I guess we could just do that. There we go. So once again, we have an equation with two unknowns. There's not a unique solution to this equation, so we can't just solve for x and say x equals 0 like we did in the circle problem. But we can still solve for a variable. And which one of those is easier to solve for? Y. Very good. I would agree. So y would equal negative 4x. I'm going to box this up for two reasons. I'm going to use this first of all to get my original equation in terms of just x. And then if they ask me for the y values, I'm going to come back to this at the end and plug in to find them. So if I plug that into the original equation in the top right there, I get a 2x squared plus x times y, which is negative 4x, plus 4y squared, which is negative 4x, quantity squared, and that equals 3. So I plugged this guy right here, on the far left, back into the original equation on the far right. That's the other way to relate x to y. And now you got it in terms of a single variable. And notice it asked you to determine the x values only, so I don't really need to come back at the end and find the y values. My expression is already in terms of x, so if I just solve that equation, I'll be done. Now, it looks like it's going to be kind of intimidating, but they are designed to work out pretty nicely if you don't have a calculator. So carefully simplify, especially that last term. You're going to get a positive 16 times a 4, which is positive 64x squared. And now you have a bunch of like terms. They're all in terms of x squared, so you're going to get a 62x squared equals 3. And if you divide by 62 and take the plus or minus square root, you'll get the square root of 3/62. And 62 is not divisible by 3 because its sum, 6 plus 2, is not a factor of 3. Or a multiple of 3, I should say. So that's it. If they told us to find the y values, then all you have to do is take each of those and plug it back in there. So you could then pair them up, a positive x with a negative y and a negative x with a positive y. So more than likely, when they set it up so it's easier to solve for y in terms of x. That means your answers are going to be in terms of x. More often than not, they ask you to find that value. So if you solve for the easier one, you're probably going to be done at the end and not have to find the other value. So that's what those values are right there. And I'm guessing they're pretty close to 0.2 and negative 0.2. But I certainly couldn't have come up with these on my own without the help of calculus. All right, go ahead and do the same thing for part B now on your own. Determine the y values of any vertical tangent lines. And I'll go ahead and do the work up here quietly along with you all so we can compare answers at the end. Practice your notation as well. Your free response question, by the way, on the test on Wednesday will be similar to this one. You gotten plus or minus square root of 3 1/24. Again, the notation, you say dy dx is equal to non-zero over 0. That means infinity. That means then you set the denominator equal to 0. Can solve for x a lot easier than y, so we go ahead and do that. Plug that then back into the original expression for x, and that gives everything in terms of y. Simplifying carefully, 128 minus 8 plus 4 is 124 y squared. Divide, square root both sides. It comes out to be about plus or minus 0.15. And because it did ask for the y values, we're done right there. If we needed to find the x values, we'd plug both of those in right there. But 0.155, I drew them over here. If you look at it, these are like 0.1, so somewhere right in here, about halfway between 0.1 and 0.2. If you were to go straight across, it would line up with that. So pretty good. You can eyeball it, maybe get it down between 0.1 and 0.2, but can't really get as accurate as you can if you actually did the math. So anyway, there you go. If you understand this problem right here, problem number 7, or 8, sorry, you're well on your way to getting the whole back of the free response on your test on Wednesday. It'll be very similar to this. Okay, any other comments or questions on this one? All right, 2 things here. The last thing we'll finish with the second derivative. Number 9, it says to determine the equation of a tangent line of this function at that point. Well, what do we need for the equation of a line? A slope and a point. And notice they already gave you the entire point. So you're really halfway there already to write in the equation of a line. Before you even start, you're halfway there. All we need is the slope at that point. We just need the derivative of y with respect to x at the point 3, 1. How hard could that be? Well, let's see. First of all, it's not solved for y, is it? Do you want to solve it for y? Probably not in this section. So I think we're going to take the derivative implicitly. So d dx of the left side, x squared plus y squared, quantity squared, there's no reason to expand that out, equals d dx of 100xy. How many dy dx's will we have in our answer after we differentiate? 2, right? Okay, good. So the first one is a chain rule, right? It's 3 blob squared. So it becomes 6 blob to the first power times the derivative of the inner layer, which is 2 terms. So when you're doing the chain rule, if you get in the habit of putting dot parentheses, you're less likely to make a careless mistake. You get 2x dx, or just 2x, plus 2y dy dx. And that takes care of the left side. Now on the right-hand side, you have 100xy. So you do have a product rule, and remember, you can associate the 100 with the x. It's a lot easier than considering as its own separate function, and some people factor out the 100 and then have parentheses with the xy. It's probably easier just to keep it as 100x times y. So with that in mind, we'll go 100 is the derivative of 100x times y, plus 100x times the derivative of y with respect to x, which is dy dx. And there you go. We have our 2 dy dx's from our 2 y's. The guy on the far right, he's all ready again to cavort and commingle with other dy dx terms. However, the dude on the left, he's trapped. He's trapped inside. He's trapped inside. And he can't go outside until he does all the chores his wife wants him to do, or until we distribute and spring him loose. I'm sorry. That wasn't supposed to come out. All right. So let's distribute, kind of like we did in the warm-up. We have 6 times 2x. That's a 12x times the x squared plus y squared. There's no sense in distributing all that. Plus the 2y dy dx times 6 is 12y dy dx times the quantity x squared plus y squared. This is not fun, is it? This is a lot of algebra. And even if you like algebra, you might be saying, whoa, too much of a good thing. So let's back off a little bit. Are we after the equation, dy dx, or are we just after a numeric slope? We're after the numeric slope, and we are finding it on our own accord. So if the equation said find dy dx, we could finish doing this algebra. But because we are only after a numeric slope, remember what we said at the beginning of the lesson? It's probably easier, if you're only after the numeric slope, to plug in first and then solve. So what we were doing is not wrong, it was just unpalatable. So I'm going to kind of get rid of that and come back up and say, oh, let's plug in a 3 for x and a 1 for y immediately. But since it's not solved for dy dx, we just say at the point 3, 1. And that's enough to indicate your method. Now we can plug in, and we get 6 times 3 squared is 9, plus 1 squared is 1. Times 2 times 3 is 6, plus 2 dy dx, this is already looking better, equals 100y, that's just 100, plus 100 times x, that's 300 dy dx. So look how much more user-friendly it is. If you're only after the numeric slope and you're using it one time, it probably is worth plugging in first and then solving. So we end up with 60 that we're distributing. Let's go ahead and do that in our head. This whole thing here is 60. We're still distributing, but 60 times 6 is 360, plus 60 times 2 is 120. So we have 360 plus 120 dy dx equals 100 plus 300 dy dx. And now, since I eschew negative terms, I'll bring the 120 to the right and the 100 to the left, and you end up with 260 equals 180 dy dx. And then you round, or divide, sorry, and you get dy dx equals either 260 1/80ths, or 26 18ths, or 13 ninths is the simplified version. So if you need dy dx, embrace the algebra, expand it out, solve for dy dx in terms of x and y. If you're only after a numeric slope, it's easier to plug in immediately after you take the derivative. Things combine a lot more quickly. All right, so now we're not done, right? We finished the second half of the info. They gave us the point. All we needed was the slope, and now we just drop it in. Bless you. So the equation of the line in Taylor form is y equals the y value of 1 plus the slope that we just found, 13 ninths, times x minus the x value they gave us, which is 3. That's the tangent line equation. Since we're right here, for free, let's go ahead and list the normal line equation. What's the only difference? The slope, right? It's no longer 13 ninths, but rather negative 9/13. Good. All right, so that's why I did that one. It's very similar to the warm-up. If you wanted to solve for dy dx, distribute the variables, but since you're only after numeric slope, look to plug in first. You still show it. Remember that. You still show it, but you get to your answer a little bit more quickly. Okay, the very last question in this section is example 10. And it's asking us to find the what? That's the second derivative. That's Leibniz notation, the second derivative of y with respect to x. So we're going to have to go through the first derivative. So if we come over here, we could solve this thing for y. It wouldn't be that difficult. There's only one term with a y in it, but it's y squared. It would require plus or minus. So again, that's two equations. You don't want to keep track of when to use which one. So let's just take the derivative implicitly. We have that technology, if you want to call it that, the ability to do so. So d dx on both sides. So we get 6x squared minus 6y dy dx equals 0. We only have one dy dx. Now here we have a fork in the road. We have two options. Option 1, we could take the derivative of both sides with respect to x again. After all, we didn't solve for y in the beginning. Why would we want to solve for dy dx now? Or the other fork is we could solve for dy dx first and then take the derivative of both sides. Which one do you think is going to be faster, more efficient? I dare say more fun. The first one? Let's see. Let's actually do it then. If I take the derivative of both sides with respect to x as it sits, that's going to look like this. The derivative with respect to x of 6x squared minus 6y dy dx equals d dx of 0. Okay, so that's going to give you 12x, and now I have to use the product rule. I have negative 6y and dy dx. So that's going to be negative 6 times dy dx times dy dx. And then minus 6y times the derivative of dy dx, which is what? d squared y over dx squared. And all that equals 0. Now I can solve for the second derivative. Notice this right here. This is dy dx squared. That's the first derivative squared. And this is the second derivative. If you noticed, it said up here to find the second derivative as a function of x and y. So if I just go ahead and solve this for the second derivative, I'll have it in terms of x and y and dy dx. Guess what I'm going to have to do to get rid of dy dx? I'm going to have to plug what dy dx is in terms of x and y, which means I'm going to have to solve this dude right here for dy dx. And if you're going to have to do it anyway, if you do it that way, you should do it first. In other words, this is not the way you want to do it. It's not going to be palatable. So even though you can't solve the original equation for y, if you're trying to find a higher order derivative, it's always best to solve for dy dx first. Look what that's going to be. You can almost do that in your head. dy dx is going to be x squared all over y. That's what dy dx is. Okay? You can verify it by showing more steps. Then you could go ahead and plug x squared y in for both of those dy dx's and solve for the second derivative. Or, look what we could do. If we knew we were going to have to solve for it anyway, solve for dy dx first, and now just take the derivative of both sides with respect to x. You get d dx of dy dx, and then you get d dx of x squared over y. Well, the left side, the derivative of the first derivative, that's just the second derivative of y with respect to x. So notice it's already solved for the second derivative. That's good. And now on this side, we do the ho-d-high rule. Ho, d high, minus high, d ho is dy dx, all over ho ho. It's a lot easier. Now we're still not done. This gives you the second derivative in terms of x, y, and dy dx. And most of the time, when you read carefully, you'll have to find it as a function of x and y. So how do I get rid of dy dx and replace it with something in terms of x and y? Yeah, I just plug it back in. I have already solved for dy dx. You just plug in x squared y over y for that. So as we do that, we'll go ahead and simplify. The first term is really 2xy. Now it's minus x squared times x squared over y, in that term only, all over y squared. Now at this point, you could stop. You've met the requirement. You found the second derivative, which later on is going to be meaningful. It's not just acceleration. It's going to give you the curvature of the graph, and you have it in terms of x and y. But if you had to use it, or this was a multiple choice question, it wouldn't be a complex fraction. So how can we quickly eradicate the complex fraction? Multiply by what over what? Y over y. Good. That's the only miniature denominator there. If you distribute then into the numerator, the second derivative is 2xy squared minus x to the fourth all over y cubed. And that is the cleanest, nicest looking second derivative out there. So, to summarize, whenever you have to take the second derivative implicitly, you can read all that up here. It says the same thing. Even though you can't solve for y in the beginning, it's going to be a lot more efficient, less likelihood of making a careless mistake. You're going to be able to do it faster if you solve for dy dx first, explicitly, dy dx in terms of x and y, and then take the derivative after that. You'll still need to probably replace dy dx with something, but you'll already have it done. Whereas this over here, this is just going to be kind of a lot to keep track of. Okay? And that's it. That takes care of implicit differentiation. We're going to implicitly differentiate again later on when we get to the related rate section. We're going to be taking the derivative of both sides, not with respect to x, but with respect to t. And there's not going to be a single t in any of the equations. So everything's going to get a d variable dt. Yeah, it'll be a lot of fun. All right, any questions or comments on 2.7? Your quiz? Yeah, I think your quiz tomorrow, I'll probably give you one like example 7. So this will be similar to your quiz, and it's also similar on the following day to your free response. Okay? And I think there's a couple of tests up from the old tests on that web page for 2.1 through 2.7, which is Oh, no, not like example 7. Yeah, like example 8. Example 7 was also similar to example 8, but example 7 was way too easy. Example 8 is a lot more fun. Yeah. Okay? Because you'll have 2 variables, and you'll have to solve for one of the variables and plug into the other. You will not have to sketch the graph. In fact, you are trusting the work now that you're going to be able to do it entirely analytically with the equation.